This video, we're going to look at just some energy basics from honors chemistry. I know this was at the time when we transitioned to distance learning, so I think this could be helpful. Here's the question. How much energy is needed to convert ice at negative 20 degrees Celsius to steam at 120 degrees Celsius? Well, it depends on how much ice you have. So let's rephrase that question. How much energy is needed to convert 100 grams of ice at negative 23 degrees Celsius to steam at 120 degrees Celsius? Okay, so we're going to assume this is 100 grams. Now we'll solve this problem. Let's take a look at this diagram. There's no labeled axes, but I'm hoping you're figuring out this is temperature in degrees Celsius. And this would just be adding time gradual or adding heat gradually over time. Let's look at what's going to happen. I'm starting with ice at negative 20 degrees Celsius. The molecules are vibrating. They're going to vibrate faster, 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 faster till I get to 0 degrees. Now there's too much kinetic energy for them to be held in the solid state. And what they do is they melt. And when they melt, instead of a kinetic energy change that we experience as the temperature rises, now it'll be a potential energy change as it goes from B to C. So at B, it's liquid. At B, it's all ice. At C, it's all liquid. And between B and C, we have ice water. If it's thoroughly mixed, the temperature should remain at 0 degrees Celsius as it's melting. Once it's all melted, now the molecules slide over each other faster and faster and faster and faster till I reach D, and that would be 100 degrees Celsius. At this point, the molecules go from a liquid to a gas. D is all liquid, E is all gas. Here is where it's boiling, and again, just above the water level, or you're going to see that 100 degrees Celsius at the boiling point. Okay, again, it takes energy for molecules to break their attraction in the liquid state to go to a gas. Essentially, we have to separate the water molecules, and this is actually a very big amount of energy with this phase change right here. Finally, once it is all a gas, then the molecules can move faster and faster, and it's kinetic energy change until we get to 120 degrees. So that's theoretically what happens. Let's take a look at the mathematics in solving this. There is a slope formula for sensible heat because it's reflected in temperature change. And that formula is energy equals C, which is the heat capacity, times M, times the mass of substance, times the change in temperature. Okay? And the heat capacity of water is 1 calorie per gram degree Celsius. However, for ice or gas, it is different. So from going from A to B, remember A to B is this change from negative 20 to 0. Down here, it is going to be the heat capacity of ice, which just so happens to be 0.50 calories per gram degree Celsius. That would be given to you. I think it's actually in your homework packet units there. So that is the heat capacity of ice. We set 100 grams, and we said it went from negative 20 to 0. So we multiply that. If we're doing this in calories, we get 1,000 calories or 1.0 kcals. Okay, going from C to D, I'm not going to go back up to that diagram, but that is a heat capacity of water. It's 100 grams, and this is the part when it went from 0 to 100 degrees. So notice we had double the heat capacity, 5 times as much temperature change. So we have 10 times as much calories or 10 kcals. And finally, the E to F, this is the heat capacity of the gas. We had 100 grams, 20 degrees, we get 900 calories or zero 0.9 kcals. So let's just do a quick summary of those slope formulas, and we plug those in up here. And that's where I got this 1 kcals and the 10 kcals and the 0.90 kcals, A to B, C to D, E to F. we still got to account for the plateaus, and you're going to see that that has quite a bit of energy changes is stored in phase changes. So let's look at the plateau formula, and you have N times delta HF or N times delta HV, and N is the number of moles, and then delta HF is referring to the change in heat content for either freezing or melting, which is the same, but sometimes you're absorbing energy, sometimes you're giving off energy. B is for vaporization, but you can think about that as vaporizing or condensing. So the lower plateau is delta HF, the upper plateau is delta HV, and you'll be given values in either calories per gram or calories per mole, okay? And what happens is I took my 100 grams, converted that to moles. And then what I did was going from B to C, which was the lower plateau, I took my moles times 1.44 kcals per mole. This was given, this is delta H, delta HF, okay? And I get 8 kcals. And then I did the same thing for D to E for the upper plateau, except this was 9.7 kcals per mole. So notice this is a lot bigger. The upper plateau is a lot bigger than the lower plateau. Looks like between 5 and 10 times bigger magnitude. That's typical for most substances, because what happens when you go from a liquid to gas, you actually have to have the energy to completely separate the molecules from each other. Not just break the attraction in the solid state to go to liquid, but that complete separation you're trying to get going from liquid to gas. So let's just go back, look at our energies right here, and we can see that the 8.0 goes here, the 53.9 goes here. And if we add all these things up, let's see, I think we get what? This is from the slope, the 1, the 10, and the 9, or 0.9, adds up to 11.9. And the phase changes, look at all that energy there, and ultimately we get 73.8 kcals per mole. So you think about a lot of heat systems, and what are they trying to do? During the day, they're trying to absorb energy and cool things down. So they're actually going through a phase change, either solid to liquid or maybe liquid to gas. And then at night, they end up condensing or freezing, and they give off energy, providing heat. So sometimes trying to take advantage of these principles of these phase changes in doing that. All right, hope this helps in reminding you of the first things about heat. Thank you.